All right, so Venn diagrams. So this is a way to give us a good visual of exactly what we're looking at when we're talking about sets. And so we can do these with any amount of sets, but we'll start with just two sets. So first, if we look right here, we just have the set A that's being shaded in. And notice that there's a little bit of overlap with B, and the same goes for when we look at just set B. So now if we want to consider the union of those two sets, remember that the union is everything from A and everything from B. The intersection the little middle piece there is going to be the intersection. So next we'll consider the difference, A minus B. So remember that's everything in A, and we're taking out everything that exists inside of B. All right, so there's A minus B. Now we want to consider the symmetric difference of A and B. So that's everything in A or B, but not both. All right, so there is the symmetric difference of A and B. So remember that A complement is everything outside of A. So if we shade everything outside of A, we disregard B, this would be A complement. And so we might be asked to do something a little bit more complicated, like A union B complement. And so there is A union B complement. All right, so definition, a set is infinite if it can be put into a one-to-one correspondence with one of its proper subsets. So let's look at Z plus, for example. So that would be 1, 2, 3, 4, 5, 6, 7, 8, and so on. And secondly, what we're going to do is consider a proper subset of Z plus. So we could say maybe 2Z plus. That's the set of even positive integers. So that would be 2, 4, 6, 8, and so on. And so we know that this is infinite. We just want to be able to show it. So we can say without a doubt that 2Z plus is a proper subset of Z plus. That's definitely true. So we're going to make a function now, and this is going to be our one-to-one correspondence, and that function will be f of n is equal to 2n. So now if we list the elements of Z plus, to n and then beyond, and then list the elements of 2Z plus, to what would be n, for 2Z it would be 2n, and then beyond, then we can see that the one-to-one correspondence is going to happen. 1 basically maps to 2, 2 maps to 4, 3 goes to 6, 4 goes to 8, 5 goes to 10, but more importantly, n maps to to 2n. And so that means that there's a one-to-one correspondence between z plus and 2z plus. And that means that it's infinite. But since they're having this one-to-one correspondence, it also means that they have the same cardinality, and that 2z plus must be denumerable. All right, so we're going to talk a little bit about cardinal numbers. When we consider a cardinal number, that's just basically the cardinality, the number that we get, so the number of elements. And so when we talk about finite sets, it's pretty easy. But we're looking now at these infinite sets, and it can be really tough to figure out, okay, well, z must have a cardinality of infinity. Well, that's not a real number. We can't say that. Same reason in calculus, you can't say that a limit is equal to infinity formally, because that's not a real number. We define a limit as a real number. So once you get to infinite limits, you're kind of cheating a little bit and changing the rules. But for this, we can't. There's no way to do that. So let's look at the cardinality of z plus, or even the natural numbers, if we included 0. So we don't have a cardinal number for z plus, so we're going to define a transfinite cardinal number. All right, so we know that if cardinality of A is equal to, let's say, n, the cardinality of the power set of A is going to be the number of subsets of A, so that would be 2 to the n. So that means that the power set is always going to have a larger cardinality than the set itself. And that's fine. So what would the cardinality of the power set of z plus be? So it's a weird question because this aleph naught is sort of describing the infinitude of z plus. But now we're saying we're going to take the power set of z plus. And that would be 2 to whatever the cardinality is, so it would be aleph naught. And so we call this thing aleph sub 1. But remember that the cardinality of the power set is always larger. So really, we're saying that the cardinality of aleph sub 0 is less than the cardinality of aleph sub 1, both of which designate some type of infinity to this symbol. And so what that means is we have 2 levels of infinity here. This infinity is less than this infinity. And we know that's true because one is a power set and one's not. So now what if we consider the power set of the power set of z plus? So the cardinality of that is going to be 2 to whatever the cardinality is of the power set of z plus, which is 2 to the aleph naught. And that would be 2 to the aleph sub 1. And we're going to call this thing aleph sub 2. And so we're creating this nesting of infinities here by considering power sets. One more, if we add the power set of the power set of the power set of z plus, its cardinality would be 2 to the 2 to the 2 to the aleph naught, and that would be aleph sub 3. So what we just did was we created right here levels of infinity that we didn't know existed prior to defining the cardinality of z plus to be infinity. A form of infinity, I should say, since we said it can't be equal to infinity.